Another simple harmonic oscillator is a spring oscillator. And a spring oscillator will exhibit simple harmonic motion, or SHM. So if we consider maybe a wall and a nearly frictionless surface, we attach a spring to that wall, and then we attach a mass to that spring so that it is connected, and then we displace the spring by a change in position here. Our spring will be stretched out now, and our mass will now be located here. Now, the mass located there will experience a force on it from the spring to the left, so that would be the direction of the spring force. So, if we were to let this go, it would oscillate back and forth. So let's look at a case where we have an oscillator. In this case, the object is oscillating vertically from its equilibrium position. We can see that the position is changing, and as it goes up, position down, up and down. So this is a lot like the pendulum that we looked at before. That pendulum had a cosine function for the position. Now let's look at the velocity. And the pink arrow represents the magnitude and direction of the velocity. Notice that the velocity is a maximum as it's passing through the equilibrium position here, and it's a minimum at the maximum positions. And this is our velocity curve here that shows me the greatest speed, greatest speed, greatest speed, greatest speed, and it oscillates between those. And we can also look at acceleration. So let's do that. And notice that our acceleration is the greatest when we're at the maximum position. So in general, the behavior of the mass on a spring is very similar to the pendulum. So we can describe the position of the object that's oscillating while connected to the spring as also having a cosine function here. And this would be a positive cosine function. And again, that cosine function has to be evaluated at an angle, and we can use omega to describe the angular frequency. So you can think of that as how often the object completes the cycle. So angular frequency is also known as the angular speed. They can be used interchangeably. And then we have our velocity versus time graph. Now we have a minimum velocity initially. So if you think about using the slope of the line here, so the slope of the line initially is 0. So that will give me an initial velocity of 0. And then as it passes through, as the object passes through the equilibrium position, I have a very negative slope there. So I'll have a negative velocity. And then again, here there is a 0 velocity, and we repeat that pattern and we get this negative sine curve just as we saw before. And so remember, the velocity is the derivative of the position function, and that would give us negative a omega sine of omega t. Again, that omega is still the same as this omega there. It's the angular frequency. And then last, we can look at what happens with the acceleration of this object as it is moving. And the acceleration initially is the slope of the line here, the slope of your velocity graph, which is very negative. And so I'm going to start out by having a very negative acceleration here. And then our acceleration is 0 there, the slope of the velocity time graph. the acceleration. So then we can continue to graph our acceleration here and have a 0 acceleration, and then again it'll pass through here, and the acceleration then would be very positive. That's a very positive sloped line there, and so it would be very positive acceleration, and then 0, and then a very negative one again, and we get this negative cosine curve. So our negative cosine curve matches with the derivative of our velocity graph, and so the acceleration with respect to time would be negative a omega squared cosine of omega t. And again, that omega is the same omega there. It's still the angular frequency or the angular speed. And just like for a pendulum, that angular frequency or that angular speed is related to the period. Remember, the period is the time for one complete revolution. It's being 2 pi over omega, or the frequency being the reciprocal of the period, omega over 2 pi. So omega is related to the cyclic nature, and 2 pi radians is the number of radians that an object traces through in one cycle. So now let's go back and look at that restoring force now that we have looked at all the. So when we're at a maximum displacement, our restoring force is the spring force, which would be Kx. And I'm going to let x be equal to a, or the amplitude of the motion. And when we're at a maximum change in position, a maximum position, we have a maximum acceleration. So I'm going to set that equal to ma, and this would be our maximum acceleration. Now, from our equation for acceleration with respect to time, we saw that the acceleration with respect to time is equal to negative a omega squared times the cosine of omega t. And when acceleration would be a maximum when the cosine function is 1. And so we get negative a omega squared. Again, that negative sign indicates direction. So if we're just looking for the magnitude of the acceleration, we can take the absolute value. So that means that my maximum acceleration, so A maximum, the magnitude of the maximum acceleration is the amplitude times omega squared. So if we substitute this back in for our acceleration here, we would get that k times a, remember x is the maximum position, so amplitude a is the maximum position, times m, and then capital A again for amplitude times omega squared. So I'm making my substitution here, and I can do some algebra, divide by the amplitude on both sides, and I get that the angular frequency is the square root of k over m. And that should look a little bit familiar because we know from our lab that the period is 2 pi root m over k, which would mean that the period is equal to 2 pi over omega. So just like before, the angular frequency described by our cosine or sine function is this root k over m for a spring oscillator.